The paper we're diving into today is P does not equal NP proof by Andre Luis Barbosa. So right off the bat, this is one of those titles that really sets expectations high. I mean, P versus NP is like the holy grail of computer science, right? It's one of those Millennium Prize problems.
Exactly. And Barbosa is claiming to have a proof that P is not equal to NP. That's pretty huge if true. For anyone not steeped in the jargon, P versus NP basically asks whether every problem whose solution can be checked quickly can also be solved quickly. And the significance is, well, just massive. Like, it underpins cryptography, algorithms, pretty much all of computer science.
Yeah, and you know, the Clay Mathematics Institute is offering $1 million for a solution. Not to get lost in the money or anything, but this is one of those problems where if someone really proved it one way or the other, the whole field would kinda have to recalibrate.
So Barbosa's approach is actually a bit unusual. He doesn't just tackle the classic definitions of P and NP. What he does is generalize them. He argues that our standard notion, that decision problems are always formal languages, is incomplete. Instead, he introduces what he calls LZ languages, which are a more general way to describe decision problems. The idea is that not all problems can be modeled as classic languages.
And that's where his artificial problem comes in, the XGSAT. He constructs this as a kind of harder version of SAT, the classic Boolean satisfiability problem. But in XGSAT, you're given a restricted type X program and a number n, and you have to decide whether the program returns 1 for at least one input of length n.
Right, and the catch here, the crucial detail, is that for each restricted type X program, there is a polynomial time bound for all n-bit inputs, but you don't know what that bound is in advance. It's fixed for the specific program, but not across all possible programs. So, like, you can't write a one-size-fits-all solver.
Exactly. So in a sense, you can verify a positive answer quickly if someone hands you the right input. But actually finding that input deterministically could take, in the worst case, exponential time. That lines up with the intuitive difference between P and NP, doesn't it?
It does. What Barbosa then argues is the XGSAT problem, under his generalized definitions, is in NP but not in P. He goes through all these possible ways a deterministic algorithm could try to solve XGSAT more efficiently. And each time he says, nope, eventually you're back to brute force.
Yeah, and that's an interesting twist. He uses diagonalization arguments and even invokes Rice's theorem to block certain attempts to decide XGSAT in polynomial time. But, and here's where I started scratching my head. I feel like the proof hinges heavily on redefining the core classes and then sort of showing separation under those new definitions.
That's fair. I mean, he also pushes back against cornerstone theorems like the Cook-Levin theorem, arguing it's incomplete or even false for his generalized NP. That's a big claim. But the field has, for decades, treated those results as bedrock. It's hard to know how much, you can move the goalposts and still be playing the same game.
I think it's brave, though. Barbosa even says he expects to be seen as crank or crackpot, but he's motivated by, a desire to force a deeper look at what these complexity classes really mean. And to his credit, academic research is supposed to be about challenging assumptions.
Totally. Even if the community doesn't buy all of his generalizations, the paper prompts us to reconsider how we define problem, language, and complexity. I mean, definitions sometimes do catch little subtleties that change how we classify things.
Also, the discussion of promise problems and LZ languages, it reminds me a bit of when I was trying to explain promise problems to my roommate and realized I couldn't even define a promise without going down a rabbit hole about input restrictions. Actually, I never even got to the point. My roommate just gave up and started playing chess.
Yeah, complexity theory isn't exactly coffee table banter. But for listeners, what's at stake is that the tools we use in real computing, be it cryptography, optimization, or AI, are shaped by what's easy or hard according to these classes. Barbossa's work kind of spotlights those boundary lines.
And you know, research isn't the same as gospel truth.
Welcome to In Depth with Academia. I'm Richard Price, CEO of Academia EDU, and, well, today we're diving right into one of the great, mind-boggling questions in computer science, something that's been on the minds of mathematicians and programmers, and really anyone nerdy enough to love a good puzzle for, decades. I'm talking about the P versus NP question, and more specifically, we're exploring a paper by André Barbosa titled PNP Proof. As always, I'm presenting this paper neutrally. I'm not endorsing it, but rather sharing what the author is arguing, so you, dear listener, can think critically and draw your own conclusions. So what is this paper about? Let's just start there. Barbosa tackles the famous question: is every problem whose solution can be quickly verified also a problem whose solution can be quickly found? In technical jargon, is P equal to NP? Or, put another way, can computers efficiently solve all problems that they can efficiently check? This is so significant. There's $1 million Clay Mathematics Institute prize riding on this, and it has implications for everything from cryptography to scheduling to Sudoku puzzles. Literally, the security of your online banking might hinge on that little symbol. Barbosa claims to prove, wait for it, that P is not equal to NP. That's a massive claim. How does he go about this? Well, his approach is sort of unconventional. He starts by pointing out what he sees as a limitation in how the computational classes P and NP are traditionally defined. Usually when computer scientists talk about decision problems, they model them with what we call languages, not English or French, but sets of strings that represent yes or no answers. Barbosa says, hey, not all decision problems can be squeezed into this language framework. He introduces a generalized concept, the ELS language, which is just a fancier, broader way to talk about decision problems. It's a bit like saying, let's count all fruit, not just apples, okay? So then André Barbosa constructs what he calls the XG-SAT problem, which is essentially a generalization of the classic SAT problem but designed to be even slipperier, even harder, given this new perspective. He defines a special kind of program called a restricted type X program with certain behaviors and time bounds. The heart of the proof claims XG-SAT is a problem that lands safely in NP, meaning we can verify a solution quickly, given the right certificate, but crucially, it can't be solved in polynomial time by any deterministic algorithm, so it's not in P, therefore, boom, P, NP, QED, if you accept all his new definitions and constructions. So let's pause. What does that mean for you, the curious listener? If Barbosa's logic is valid, it would mean that for some problems, one similar to XG-SAT, no matter how clever you are, no matter how massive your computer, you'll never find a fast, general-purpose way to solve them, though checking if someone else's answer is correct might remain fast. That distinction literally underpins the world of cryptography. But here's the thing. Barbosa's proof is based on all these generalizations. He actually claims things like the Cook-Levin theorem is false, which, whoa, is about as heretical as you can get in theoretical computer science. If you ask mainstream researchers, most would strongly disagree with his definitions and, well, the legitimacy of his approach. Let's talk methods for a second. Most of the paper is taken up with these careful incremental constructions, redefining what counts as in NP, showing XG-SAT fits those definitions, and then arguing in great detail that no deterministic machine can solve XG-SAT in polynomial time. He uses some diagonalization arguments, draws on undecidability via Rice's theorem, and examines what happens if you try to game the system and shortcut the problem. He claims, nope, you can't do it. The paper even argues it sidesteps known barriers to resolving P versus NP, like the relativization and natural proofs obstacles. Now, honestly, there's a lot here. Barbosa's proof hinges on whether you buy his more general definitions. Mainstream theorists, as I said, mostly don't. But even if you think the proof doesn't fully land, it's still intriguing. Barbosa's work is a reminder that the foundations of computer science are not set in stone. Definitions matter so much. If you shift the sandbox, sometimes the rules and the outcomes change. And hey, little digression, this reminds me of those times people argue about, board game rules, and someone pulls out an official definition from a tattered rulebook, and everyone else just says, "No, we play it this way at my house," which goes to show definitions aren't always as absolute as we might wish. Anyway, before we close, what should you carry away from Barbosa's paper? Whether or not you're convinced, it's a call to approach accepted truths in academic fields with curiosity and even a bit of skepticism. Don't just take anyone's word for it, especially not when the stakes are this high. Academic research is a conversation, not a decree. Barbosa is challenging the status quo, but that doesn't mean his view is now the truth. For you, whether you're a student, teacher, or just a fan of big puzzles, it's about being open to new ideas, knowing limitations, and appreciating the ongoing adventure that is scientific discovery. That's all for today's episode of In Depth with Academia. I'm Richard Price, still refusing to say the final word has been spoken on P versus NP. Thank you so much for listening. Stay curious, ask questions, and don't forget, in academia, the answers are never quite as fixed as we might wish. Take care. Are deterministic algorithms really outpaced by non-deterministic ones? In this groundbreaking proof, Barbosa challenges traditional P versus no problem assumptions by redefining complexity through XGSAT. Barbosa defines a restricted type X program as one that, given any n-bit input, either returns 0, 1, or does not halt, setting the stage for constructing XGSAT. XGSAT generalizes SAT by questioning whether a restricted program returns 1 for at least one n-bit input. This approach broadens our view of computational decision problems. To decide XGSAT, a deterministic machine must simulate all possible inputs, yet diagonalization and Rice's theorem reveal inherent limitations, forcing brute force search and exponential time. Every deterministic strategy, whether simulating every input or selectively sampling, ultimately fails to decide XGSAT in polynomial time. This proof unifies complexity and computability theories. Barbosa's revolutionary proof challenges traditional complexity definitions, urging us to boldly rethink our computational limits, embrace critical examination of long-held assumptions in theoretical computer science.